Good morning, students, and welcome to another video lesson. Today we shall be discussing the topic of behavior of perfect gases. Now, you might be having an elementary knowledge about the concept of thermal expansion. The expansion which takes place due to supply of heat energy is called thermal expansion. This expansion may be in terms of length, area, or volume. Now, in the case of gases, thermal expansion is very large as compared to that of solids and liquids. It is found that the volume of a solid or liquid practically remains the same even when a large pressure is applied. However, the volume of a gas changes appreciably when its pressure is changed even by a small amount. Therefore, to describe the condition of a gas, its volume, pressure, and temperature must be specified. A change in any one of these quantities affects the others. The gas laws are the study of the relation between any two of these quantities when the third is kept constant. The three gas laws are the studies of number 1, effect of pressure on the volume of a given mass of a gas at constant temperature. Second, effect of temperature on the volume of a given mass of a gas at constant pressure. And number 3, effect of temperature on the pressure of a given mass of a gas at constant volume. Let's begin with Boyle's law. This law was discovered by Robert Boyle in 1662 and it is one of the most fundamental gas laws. It states that the temperature remaining constant, the volume of a given mass of a gas is inversely proportional to the pressure. So mathematically, if temperature of the gas is constant, then volume is inversely proportional to pressure. Or we can write down PV equal to constant. In general, if P1 and V1 are the initial pressure and volume of a gas and P2 and V2 their final values, then we can write down P1 V1 is equal to P2 V2. Mathematically, Boyle's law can be expressed in another form also. If the given volume V of the gas contains n molecules, then number of molecules per unit volume given by small n will be equal to n by V, or we can write down V to be equal to n by n. So we can write down P in terms of V, we can write down n by n equal to constant. Now since n is constant, so we can write down P by n to be constant. So in general, if P1 and N1 are the initial pressure and number of molecules per unit volume and P2 and N2 their final values, so we can write down P1 by N1 equal to P2 by N2. Now this is the graph between pressure and volume at temperatures marked on the graph. Now from the graph we can conclude that at low temperature and high pressure there is a little bit of a deviation. We can say that gases do not obey Boyle's law strictly at all values of pressure and temperature, but are found to do so only at the low pressure and high temperature. Charles' law, which is also called the law of volume. Around 1787, A.C. Charles studied the variation in volume of a gas with temperature and formulated the law, which states the pressure remaining constant, the volume of a given mass of a gas increases or decreases by a constant fraction of its volume at 0 degrees Celsius for each rise or fall of 1 degree Celsius in temperature. Now let us consider a gas occupying volume V0 at 0 degree Celsius and V at theta degree Celsius. Then according to Charles' law, the volume of the gas at theta degree Celsius is given by V equal to V0 plus V0 gamma P times theta, or we can write down V to be equal to V0 taken out as common 1 plus gamma P times theta, where gamma P is the coefficient of expansion of gas at constant pressure. So we can write down gamma P to be equal to V minus V0 divided by V0 into theta. Now, by noting the volume of a gas at 0 degree Celsius and theta degree Celsius, the value of gamma P can be determined experimentally. Now, experimentally, it has been found that gamma P is equal to 1 by 273.15. So, therefore, we can now write down V to be equal to V0 1 plus 1 by 273.15 times theta. So using this expression, we can write down Charles' law in a different way. The pressure remaining constant, the volume of the given mass of a gas increases or decreases by 1 by 273.15 of its volume at 0 degree Celsius for each 1 degree Celsius rise or fall in temperature. Now, from this we can conclude that when theta is equal to minus 273.15 degrees Celsius, volume of the gas will become 0. And if the gas is cooled to a temperature below minus 273.15 degrees Celsius, the volume will become negative. Now, since the volume of the gas cannot be negative, minus 273.15 degrees Celsius is the lowest temperature that can be reached. A temperature scale whose 0 coincides with this value, that is minus 273.15 degrees Celsius, is called the absolute scale of temperature, and minus 273.15 degrees Celsius is called absolute 0. The interval between freezing and boiling points of water is also divided into 100 equal parts, just as in the Celsius scale. The temperature of 0 degree Celsius corresponds to 273.15 Kelvin on the absolute scale and is denoted by T0. A temperature of theta degree Celsius on the absolute scale will be 273.15 plus theta, denoted by T. So now we can write down V to be equal to V0 273.15 plus theta divided by 273.15, which implies V to be equal to V0 T by T0, or we can write down V by T equal to V0 by T0. This means V by T is equal to constant. So now we can say that the pressure remaining constant, the volume of the given mass of a gas is directly proportional to its absolute temperature. This is the graphical representation between V and T. Coming to Gay-Lussac's law, that is law of pressure. Joseph Gay-Lussac studied the variation of pressure of a gas with temperature and arrived at the following result. The volume remaining constant, the pressure of a given mass of a gas increases or decreases by a constant fraction of its pressure at 0 degree Celsius for each rise or fall of 1 degree Celsius in temperature. It is called Gay-Lussac's law or the law of pressure. So if P0 is the pressure of a given mass of gas at 0 degree Celsius and P is the pressure at theta degree Celsius, then according to Gay-Lussac's law, we can write down P to be equal to P0 1 plus gamma V times theta, where gamma V is the coefficient of increase of pressure at constant volume or the pressure coefficient of the gas. Now again, it has been experimentally found that gamma V is equal to 1 by 273.15. So therefore we can write down P to be equal to P0 1 plus 1 by 273.15 times theta. So now we can say that the volume remaining constant, the pressure of a given mass of a gas increases or decreases by 1 by 273.15 of its pressure at 0 degree Celsius for each 1 degree Celsius rise or fall in temperature. So we can write down P to be equal to P0 273.15 plus theta by 273.15. So this will be equal to P0 T by T0. So we can write down P by T to be equal to P0 by T0, which further implies that P by T is equal to a constant. So thus Gay-Lussac's law may also be stated as the volume remaining constant, the pressure of a given mass of a gas is directly proportional to its absolute temperature. Perfect gas equation. In practice, the gases do not obey the gas laws at all values of pressure and temperature. It is because of the intermolecular forces between the gas molecules. A perfect gas is one whose molecules are free from intermolecular attraction and obeys the gas laws at all values of temperature and pressure. Perfect gas equation. Consider 1 mole of a perfect gas. Let P1, V1 and T1 be its initial pressure, volume and temperature respectively, and P2, V2 and T2 be their final values. The change of the state of the gas from the state P1, V1, T1 to P2, V2, T2 may be supposed to be taking place in two steps. So, step 1. Suppose that the temperature of the gas T1 is constant and pressure is changed from P1 to P2 so that volume changes from V1 to V dash. Now since the temperature of the gas remains constant, so from Boyle's law we can write down P1 V1 equal to P2 V dash. Coming to step 2. Now the pressure, volume and temperature of the gas are P2, V dash and T1 respectively. Suppose that the pressure of the gas is kept constant at P2 and temperature of the gas is changed from T1 to T2 so that volume changes from V dash to V2. Now since the pressure of the gas remains constant, then from Charles' law we can write down V dash by T1 equal to V2 by T2. So we can write down V dash to be equal to V2 into T1 by T2. Now from equation 1 we can write down P1 V1 equal to P2 and in place of V dash we can write down V2 into T1 by T2. So that gives us P1 V1 by T1 equal to P2 V2 by T2. So we can write down PV by T equal to constant. Now in this equation, for 1 mole of the gas, the constant is denoted by R. It is called universal gas constant. So we can write down PV equal to RT. This is the perfect gas equation for 1 mole of gas. Now if mass of gas is n moles, then we can write down PV equal to nRT. If V is volume of 1 gram of the gas, then PV equal to R by M T, or PV equal to small r into T, where small r is equal to R by M is the gas constant for 1 gram of gas, and obviously M is the molecular weight of the gas. 1 mole of the gas at standard temperature and pressure, that is STP, occupies a volume of 22.4 liters. Standard temperature and pressure, that is STP, is also known as normal temperature and pressure. In some books it is written NT,